大家好，感谢大家在百忙之中参加极致俱乐部英国涌现读书会的报告。我是今天的主持人杨二茶，是清华大学的在读博士生。今天我们非常荣幸地邀请到了来自美国 Tufts 大学的神经科学家 Erik Hoel 教授，同时也是英国涌现理论的提出者之一，来给大家分享关于英国涌现的最新研究工作和进展，帮助大家梳理英国涌现当前的框架和可探索的课题。今天的讲座将主要用英文进行，因此接下来我将用英文进行嘉宾介绍。It is my great pleasure to introduce our distinguished speaker today, Professor Erik Hoel. He's the Research Assistant Professor of Biology from School of Arts and Sciences at Tufts University. He completed his doctoral training with Rafael Yuste at Columbia University and uses information theory and causal analysis to explore the biological basis of consciousness and understand the nature of emergence. Part of this research is on how complexity and information theory can be used to track or measure the neural difference between consciousness and unconsciousness, using data from cutting-edge neuroscientific methodologies. The goal is to develop a formal measure to consciousness that can be empirically verified and is medically useful. A second aspect of his research is to understand how causal structure changes across scale, and how information theory metrics can capture and quantify the emergence of macroscale causal structure. The goal is to improve causal model choices in scientific fields, as well as solving long-standing problems in neuroscience, such as identifying the fundamental function unit of mammalian brain. He's pursuing this by causally analyzing the cortex from the microscale of individual neurons to the mesoscale of neural ensembles to the macroscale of brain regions. Professor Erik Hoel is, besides his scientific achievements, he also had his debut novel recently, The Revolution. But today I think he's going to majorly introduce to us about his scientific achievements. Then we also have 4 distinguished guest panelists today with us. I'm going to introduce them one by one. We have Professor Zhang Jiang from School of System Science, Beijing Normal University. He's also the founder of Swarma Club. We also have Professor Yizhuang You. He's the assistant professor from Department of Physics in University of California, San Diego. Then we have the founder and director of G-Tree Institute of Deep Perception Technology, Yu Tao Yue. And the last panelist will be Sarah Walker. He's the assistant professor from School of Earth and Space Exploration in Arizona University. Now, without further ado, let us welcome Professor Erik Hoel to introduce his scientific findings for us. Welcome, Erik.
Okay, wonderful. Thank you so much for the lovely introduction, and thank you so much, everyone else, for being up at whatever time this is for you. So I'm much appreciated. So I'm going to talk today about how I think we're at the beginnings of something that might resemble the science of emergence, and I'm also going to talk about some give hopefully a broad overview, and then dive into some really recent research of mine that I hope puts some of this on firmer grounds. And so expect this to be pretty, high level. Don't think you have to understand, every single equation that I'm going to throw up on the slide. If you do, that's great. But just kind of keep a big picture overview. Most systems, I think it's well accepted that the vast majority of complex systems form spatial temporal hierarchies. So first of all, there is the spatial temporal hierarchy of the sciences themselves. So from physics to chemistry to biology to psychology, right? We're all familiar with. But also, your own computer has all sorts of different spatial temporal scales, like from the hardware level to low level machine languages to high level descriptions of your desktop. And all these seem like perfectly viable, real scales to be objects of scientific inquiry and study. And this becomes a really important question when it comes to systems that we didn't build ourselves at some particular scale to understand. So, for example, within the brain, the cortex itself, there's a lot of people who have, long-standing debates within the field about at which level, at which scale is best to kind of understand and analyze cortical function at. So is it best to understand everything that's going on down in the neurotransmitters? Is it best to kind of build your neuroimaging device up at the local field potential? Some people even think that the actual functional units of the brain aren't neurons at all, but are rather the mini columns that span cortical layers. So we have this big diversity of opinion about even where to look, what scale to look at, because of course we didn't build the system, so we don't know what scale. And it seems as if there are like objective scientific answers to these questions. And when you're talking about something like emergence, it should be clear that emergence, while it is a traditionally philosophical subject, it should be very obvious that there are, or it should be central to whatever form of emergence you're talking about, that it should have scientific impacts. It should have like real relevant outcomes. And one real relevant outcome of a scientific theory of emergence is that it tells you what scales are important to look at, right, within a system, or at what scale a system is working at, etc. So what do I mean by scale, right? So I'm going to leave it relatively loose, but I'll give you some intuitions about what I'm talking about. So broadly, the terminology that I use is that generally we're thinking about some micro scale, and then we're also going to consider some macro scale, with macro scale being some higher level, dimensionally reduced model of the system. So it's like, imagine you have one system, right, like your computer, and you can analyze it at all sorts of levels or perspectives. I do this with like networks, so things that are much smaller and simpler than your computer, right, all the time, right? So an example might be a spatial grouping, where you group together a couple nodes in a network. These might be states in a state space. They might be nodes in a Markov chain. They might even be Boolean nodes, right? They could kind of be anything here, but in general, you could group things together spatially. You can group things together temporally, even. You can even do spatial temporal groupings, right? Where you're kind of chunking the whole system. And again, another analogy might be thinking about the brain. It might be that a spatial temporal grouping is like an fMRI voxel, right? Or something like that. It's just a high level description of the system. And the key thing about macro scales is that, of course, they're smaller, right? The number of parameters that you have in your description of the system is much smaller than down at the micro scale. So this is like a fundamental feature or defining feature of what makes something a macro scale. And traditionally, what I've done is look at a particular measure. A lot of this was inspired by some of these early measures of looking at causal structure and causal function, things like the effective information, things like the integrated information. And so when you're talking about emergence, what you need is some way to measure it, right? And I'm actually gonna skip ahead here for a second. I'll go back. So basically, the idea would be that if we want to pick out scales of importance, if we want a scientific theory of emergence, then we should look across the scales to find the one that is maximally informative or maximally interesting, right? And so, I've designed some of these things that take a particular measure, the effective information, which I just talked about, and searches across scales looking for maximum of these. So the idea is something like this. So you start with some system, and again, you just think of this abstractly, right? So these little nodes could be neurons. They could be logic gates in a Boolean network. They could be nodes in a Markov chain, right? Like, think of them abstractly. You have some microscale with a lot of elements, a lot of connectivity, some system, and you're going to look at the causal structure, and then you're going to coarse grain it. And you look at the causal structure, coarse grain it again, look at the causal structure, right? So it's like we're looking through the hierarchies of the system, looking for this scale of interest. And when you do that, you have to have some way of judging what scale looks the most interesting. And I think the best way to do that is to look at how the causation in the system is distributed. And the measure that we've used so far, and exactly this I'll get into, is the effective information. So to go back a little bit on the effective information, there we go. So in the effective information, it's telling you is essentially, it's basically a measure of noise in your system. So again, think about this as a high level, but you can think about it as the amount of uncertainty that like a random walker on a network faces. So like I've got some system A, B, C, D, E. It's got 5 states. Let's say that this is a Markov chain. If I'm in state B, where am I going to go in the future? Well, I'm going to go to either state A or state C. And I can represent where my transitions via transition probability matrix. And that will look like this here in the center, where I have some transition probabilities between all my states. And what the effective information is measuring is the average entropy that being on my random walker faces, minus the average entropy of how that uncertainty is distributed. And overall, this is going to capture the amount of noise in the system. You might be thinking, I think, legitimately, how is this? What exactly is this measure like? So this measure is actually very similar to the mutual information. So if you're familiar with the mutual information, you can think of the effective information as basically the same as the mutual information, but under certain assumptions. And this turns out to be a very nice way of measuring causal structure. We've shown that it's kind of equivalent across, like it has very nice, elegant mathematical results. But I want to move a little bit past the effective information right now and just put those details aside. And again, talk a little bit more high level. So what do I mean then by causal emergence? Well, how do we know when we found this scale of interest, this good scale? Well, we can define this mathematical quantity, causal emergence, as the difference between whatever measure you've used. Again, we just talked about the effective information, but let's make it measure agnostic for right now. Whatever measure you have, it's this difference between the macro scale and the micro scale. So it's like you apply the same measure at the macro scale and the same measure at the micro scale, and you compare the difference between them. If it's a measure of causal informativeness, like the effective information, then you'll get some bit value out of it. But it doesn't necessarily have to be a bit value. It's just this difference, right? And the counterintuitive or interesting thing about causal emergence is that for some measures of things like causation, it seems as if this difference can be positive. Like you might say the basic kind of reductionist assumption would be that this measure is always negative. Like it's always better down at the microscale. Like the causation is always stronger. Whatever your measure says is going on is always kind of better down at the microscale. But that turns out actually not to be true. So it's not true with the effective information, depending on the system that you're looking at and its properties and how much uncertainty is in the system, and so on. But the clear thing should be that sometimes it seems as if the macro scale can kind of give a superior account. I don't know who just drew on my screen, but okay, I've never seen that before. It's right down here now. Okay, regardless. So there's all sorts of really cool, basically results that I can tell you about in regards to causal emergence and the effective information. The effective information was the first measure that we identified causal emergence with. We eventually also identified it in the integrated information, which is similar to the effective information. Let me give you one quick, really cool result before moving on, because again, I want to actually talk about causal emergence beyond just the effective information here. So one really cool result is that you can build scale-free networks. Some people in network who are familiar with network theory might know about scale-free networks. And it turns out that scale-free networks show both zero causal emergence and zero causal reduction. So there's no benefit at any scale for scale-free networks. And as you transition away from being scale-free, which is about this 1 on the axis, you see this huge increase in the amount of causal emergence that you get. So basically, exactly as you would suspect, like we already know in network science that people talk about scale, causal emergence tracks how they talk about it, right? So as networks stop being scale-free, they develop a signature scale according to the causal emergence framework. So we had some quite nice mathematical results like that. I'll give another one, which is here's looking at causal emergence across all sorts of networks, brains, road networks, co-authorship things. Now, a lot of these aren't actually good causal structures, so it's a bit assumptive to use a measure like. So it's really just like a network property. But just to be said, you can measure this in all sorts of things. When you look at all sorts of different networks, you find that biological networks show a lot of causal emergence. Technological networks and like engineered networks don't seem to show a lot of causal emergence. There's a paper that just came out that we just put out like a month ago that I think is really cool, where we actually show that across evolution, causal emergence has increased. Again, if you're measuring it using the effective information. So if you look at, if you basically take the protein interactome of organisms, because we have these full protein interactomes, and you treat them like they're a causal structure where proteins interact with proteins, right? You can do all the measurements on that. And what you find is that prokaryotes have very low levels and eukaryotes have very high levels, kind of maybe sort of indicating that at some point evolution figures that you can start kind of constructing your causal structure up at higher scales. So like basically it might be that in eukaryotes, the individual proteins like aren't really the right scale. It's like groups of proteins that are like the correct scale, which might explain, maybe why eukaryotes are actually notoriously difficult to understand biologically compared to prokaryotes. But so this is a very, again, kind of a cool little result, again, using the effective information. This is just an example where on the left, we've got the microscale of the gene interaction network of yeast. And we see that the effective information is 6.6 bits. At some macro scale of the same yeast network, right? You have way fewer nodes in the network. Now you have an increase in the effective information. So you see causal emergence in the yeast gene network, right? So this is again quite kind of fun and interesting, and shows what you can do with the theory. Okay, but what I want to actually talk about today is again a little bit of a bigger picture. So there's been some criticism of causal emergence, and I think all that criticism can boil down to this question, which is, what if causal emergence is just a quirk of the effective information? So basically, we have this measure, like what we're doing is we're looking across scales, right? And we have to use some measure to compare the scales. And so most of the criticism has just fixated on the measure, right? It's just said like, it's just been things like either maybe there's something wrong with the effective information. It's been, I don't like the effective information. Maybe it's unfair to even measure the macroscale effective information and compare it to the microscale effective information. A physicist, Scott Aronson, made this criticism in a blog post. A philosopher has made the criticism that maybe the effective information like isn't the best way to capture causation. I think that in general, these arguments are not very good. Like I think the effective information is actually quite a good measure. But I've been thinking a lot about this question because I really don't want the whole notion of emergence to just hang on this like one particular measure, right? Like if everything hangs on one particular measure, it's a very weak, if we want a science of emergence and it's all based off of some measure, and then people are like, well, I just don't really like this measure, or I don't know how general this measure is. And I think that those are really legitimate questions or criticisms. So I want to talk about a new paper that's coming out, should be up on the archive on Monday. And I'm going to give you hopefully what isn't a too confusing walkthrough of it. And again, I apologize for the format you're going to see this in, which is basically just me going through the paper because it's so new. So I haven't really had time to kind of condense it and make it into a really nice PowerPoint yet. But on the upside, you get to see something before it's been even published yet. So what we show, so the effective information is quite nice because it seems like it captures causation well. And I've always kind of known that it's related to other measures mathematically. So people propose various measures of causation, like how strong is a cause? That's a really legitimate question you can ask. And it turns out that if you take measures that other people invented, like not me, independent invention of all these measures of causation, and all of them show causal emergence. So every measure that I can find that I've looked at there's 12 in this paper, I think, alone. So a dozen measures, right? And they weren't selected to get positive results. They all show causal emergence, and they all show causal emergence in agreement with the effective information, like at around the same kind of system dynamics. So Macroscale, and it's I like this because it's not very elegant, but it's got teeth, right? It's like really hard to argue against 12 measures of causation, right? It's like, what are you gonna, like, there has to be something wrong with all of them, right? So anyways, so in this, I'll take you through a brief walkthrough. And again, I'm sorry for this, but ignore the text for a little bit. But I just want to talk about how all these measures are based on things that you guys probably have heard of before. And that's sufficiency and necessity. So sufficiency is just how sufficient is a cause for creating an effect or for leading to an effect, right? So, rain is sufficient to make my lawn wet, right? How necessary is a cause for an effect is how much the cause is required for the effect. So rain is not necessary to make my lawn wet. Sometimes there's a sprinkler on and the sprinkler makes the lawn wet, right? So lawn wetness, rain is not necessary for lawn wetness, but it is sufficient for your lawn being wet. So in this paper, we give formal definitions kind of within a very simple mathematical language, because we're trying to use all these measures. So we kind of have to represent them using the same formal language. And what's going to actually turn out is that all the measures are based off of sufficiency and necessity. They're all just placing sufficiency and necessity in different relationships, like ratios or differences or so on. So we call this a causal primitive, because it's something that seems like anytime you propose a measure of causation, anyone in the literature, they end up relying on these really basic causal primitives. And as I'll later show, the causal primitives can be greater at macro scales. So your macro scale can be more sufficient and it can be more necessary. And that has this trickle down effect where no matter what measure of causation you come up with, causal emergence is possible in it, right? So this is kind of the heart of the paper. And just to give you, so if you look at this top equation, this is just saying that the sufficiency of a cause for its effect is basically just the probability of producing this effect given the cause, right? So, and if you look at the necessity is the probability of not getting the cause given the probability of not getting the effect given that you did not do the cause, right? So these are very classic notions within philosophy, but we can kind of just give them a nice, simple mathematical structure to it. We can also define generalizations of the sufficiency and necessity. So again, you can just focus on this mid equation here. So the determinism of a system is just a generalization of the sufficiency of that system. So the determinism of a system is just this entropy of just like how uncertain are you given a particular cause. So if you have a cause, how uncertain am I of what effect it will have? So if I've got maximum uncertainty, then I am maximally indeterministic. And if I've got minimal uncertainty, so I know exactly what's going to happen next, then I'm perfectly deterministic, right? So it makes perfect sense with the definitions of those terms. And the determinism is basically just the same thing as the sufficiency. It has a little bit of differences, but it's the determinism and sufficiency are very similar, right? Of a system. And the degeneracy of a system is very similar to the necessity. So there's basically 4 causal primitives, which are really just 2 causal primitives, the sufficiency and the necessity, but they kind of have these like generalizations. There's probably more generalizations of the 2 original causal primitives, but for all the measures, they all use some combination of these 4. So we basically fixate on those. I'll skip past this. Okay, so basically measures of causation that you can find in the literature are all just based on these primitives. They're all just like combinations of sufficiency or necessity, or they're generalizations of determinism and degeneracy. One that you might think is not, but turns out to kind of be, is like really old notions like David Hume's, famous philosopher David Hume's notion of a regularity account, right? Where he says, okay, causation is just when two things are in constant conjunction with one another. That's what causation is. Okay, so we can formalize that. We can look at the statistical covariance between a cause and an effect, right? And give it this measure of strength. This has actually been called by other authors a Galton measure of causal strengths, since it actually resembles exactly, not just resembles, it is the formalism for the heredity of traits in biology. So that's kind of interesting. And you can convert that into like our formal language. And when you do, under certain assumptions, you get back sufficiency and necessity as being really key here. Maybe another way to preface what I'll eventually show is that if you think about constant conjunction, what things are more in constant conjunction, microstates or macrostates? I'll leave you to meditate on that. Okay, there's also things like Ellery Eel's notion of causation as probability raising. So maybe something is a cause, and the degree to what is a cause is a degree to how much it raises the probability of an event compared to its absence, right? So you can define this measure of CS Eel. So CS here just stands for causal strength. Causal strength I'm using as a general term. Depending on what measure, you might think of causal strength as causal power, causal work, causal informativeness. You know, there's basically synonyms, although it might fluctuate depending on the measure. But in Ellery Eel's notion of causation, the degree to which a cause is strong is the degree to which it raises the probability. So it's the sufficiency plus the necessity minus one is his notion. And actually, you know, in some of these measures, you can have negative causation, which you can think of as preemptive causation. You can kind of have causation that's like pushing something the other way. You can have, and I know I'm blazing through these. Again, I don't expect everyone to like be following exactly, but kind of keep just like a high level of kind of where we are. I don't know what this overly thing is in here, but we have supes, which is another notion of probability raising, but formulated a little bit of a different way. So it's very similar to eels, but now we have like we can make it into a ratio. So it's a little bit different. So it'll give you slightly different results, but it's basically the same. We have Chang's has a really popular psychological model of causal attribution, which is the idea is to look at the causal power of C to produce E. And he's basically weighting the sufficiency plus the necessity minus one divided by the necessity. So you can see that this is basically eels, but with like a different term somewhere in there. But again, it's just combinations of these causal primitives, right? So there's another one. David Lewis was a really famous philosopher in the 1970s. You may have heard of. He did a lot of work on modal realism and possible worlds and counterfactuals. He's got some great notions about causation, but he also gives an idea of causal strength, which turns out to just be a ratio between two causal primitives. Right. So again, quite similar to eels and supes. Judea Pearl, you may have heard of him. He won the Turing Prize recently. He's got a great book called Causation. That's all just like a really hardcore mathematical approach to causation. And in it, he ends up defining three measures of causation, three measures of causal strength, which he calls, I'll just use the abbreviations, the PNS, the PN, and the PS. They stand for probability of sufficiency, probability of necessity, and probability of necessity / sufficiency, but they're not those, so I'm not stressing that. But actually, it turns out that Pearl, without knowing, has rediscovered the eels and the Lewis and the Chang. So Pearl gives these as measures of causal strength, but he just rediscovers the eels and the Lewis and the Chang, right? So this is good because this is consilience, right? It's like every time people go to create a measure of causation, they end up basically creating eels, Lewis, or Chang, or supes, right? And I'm actually guilty of this myself, it turns out. In Lewis, he's got this, he basically has this kind of extra thing where you can look at the counterfactual in the closest possible world, which is a very cool idea when looking at causation. I won't really get into this, but it's again, not that dissimilar. It just has this extra thing about closest possible worlds. there's also maybe some notions that aren't quite as connected, but I think do turn out to be somewhat connected. Things like a Bitflip measure. So a Bitflip measure is the idea of like, you're measuring how much of a difference a current state or an intervention makes to the system by measuring if the system can be described like in binary terms, then you would measure like how much of a difference you make by flipping one bit of a system. So if I make one change, how many changes do I then see in the future of the system? And we kind of give our own little formalism of what this is. This isn't our, this is from actually I think a paper by Sarah Walker, who might be on the panel later. I think that she's on this paper. And so they give this, and this is another measure of causation that I think is quite nice. So we included it, but you can see some of these terms, right? Probability of E given C, that looks like a causal primitive, right? Okay. And then the effective information, which I've talked about, right? So the effective information, again, ignore most of the text, but it just turns out that the effective information is just the expectation of a modification of supes. So the effective information is just like a fancy dressed up version of one of the other causal measures as well, right? Okay, so that's all well and good, Eric. This is like a menagerie of different measures of causation, right? This is, I think I said 9. I think we eventually look at various modifications. So I think we get it up to like 12 measures of causation. So what we wanted to show and ask was just to what degree can we assess, what we wanted to address was to what degree is there causal emergence across all these measures. And so to do that, you need to specify a model and make various choices. But basically, we settled on like a really simple model, which is a bipartite model. So this is just a bipartite model of states in a Markov chain. So if you know what a Markov chain is, it's just a set. It's like an abstract description of a system of a set of states, and they just transition to one another. So a bipartite Markov chain is like I've got a group of states over here and a group of states over here, right? And then they just transition back and forth to one another. So whenever you're on this side, you always go over to this side. Whenever you're on this side, you always go over to this side. And this bipartite model is quite elegant because it kind of captures this notion of you always have causes and effects, right? It's a very simple model of causes and effects. And you can do things like where you can have a main transition. So you can have like a main cause, and then you can have like your off transitions or secondary transitions, where it's like if I'm in 0, 0, 0, I generally go to 1, 1, 1, but I might also go to one of these other states, right? And then they all have their own main effects and secondary effects going back, right? And the reason why we chose this model is that it allows us to vary the causal primitives. So it allows us to vary the determinism and the degeneracy, or the sufficiency and the necessity of the model, right? I could have the main transitions all stacked on top of one another so that everyone on this left side goes to 1, 1, 1. And then that would be that 1, 1, 1 is that all these causes are not necessary for 1, 1, 1, right? Or I could have everyone go to a unique effect on the other side, and that would mean that everyone's necessary, right? So this is a nice way to create the ability to parameterize the model. So basically, the things to keep in mind here is that we have a model. We're going to apply the measures of causation on the model, and then we're going to parameterize the model so we can add different domains of noise to the model and see what happens to the measures, right? And what's also really nice is that if you can guess what the macroscale is, right? So you can take this system and you just group one side of it into one big state 1, right? And then you could group the other side of it into another big state 2, macrostate 2. And you can just think of the model as like, actually you can think of it as a not copy of itself. So it's a not copy, right? Like it's a node that flips. It always jumps to the opposite state after every time step. So that's the macroscale description. And interestingly enough, it will always have that macroscale description, no matter how I parameterize the microscale. So whether or not my transitions are perfectly noisy or perfectly deterministic, I always have this macroscale because it's always going back and forth between the two. So we have a fixed macroscale, and then we can parameterize the microscale along determinism and degeneracy. The microscale, the probability transition matrix of the microscale looks like this. The probability transition matrix of the macroscale looks like this. And we can, again, vary the model determinism and the model degeneracy. So just a brief aside. So generally, measures of causation kind of require an intervention distribution. Now, some people say, well, that's not true because there are notions of causation like Lewis's that aren't based off of interventions. But in that case, you just substitute counterfactual for intervention. It requires a specification of like how, when you go to apply this measure, like what values go into your measure? What are the probabilities that you're looking at, right? And it seems as if there are basically three distributions that make any sense. And it's actually basically just three. So first intervention distribution is like the empirical distribution, which in a dynamical system would correspond to like the stationary distribution of states. So if we took our simple model and we ran it forward to infinity, it would have some stationary distribution. We're just letting it run. And like the probability of the system not being in its current state, right? This is the sort of reasoning that goes on all the time in these measures of causation, would be based off of this stationary distribution. Another distribution would be the maximum entropy distribution, which would just be, let's just consider all states fairly in the probabilities for measures of causation. So the effective information, almost now famously, assumes a maximum entropy distribution. It doesn't assume like a stationary. If you use the stationary, it actually turns into the mutual information, which is kind of interesting. But some people don't like this because you're applying this fairness to everything is kind of weird. And like when you know when to stop, like the actual state space of most systems is massive. So this seems a bit weird. You can also do local interventions, which is basically like a mini maxent. Like you're assessing the counterfactual space around where your intervention is. This looks a lot like David Lewis's stuff on you want to choose the minimum possible world. I think local interventions are the best way to measure causation, full stop, period. It has all the best parts of the maxent, but none of the worst parts. But again, it turns out none of this matters because it doesn't matter what intervention distribution you use. All the intervention distributions show causal emergence in all the measures. So all this has been leading up to this quite confusing graph that I will walk you through. So on each row here is the values for a particular measure of causation. So at the top, we've got the Galton, which is the Humean notion. We've got supes, Eels, Chang, Lewis, another Lewis, Bitflip, the effective information, right? So these various measures of causation. And at each graph, we're looking at the value of that measure, right, in some particular parameterization of the model. And we're parameterizing the model, again, by making it more deterministic and changing the degeneracy as well. So more degenerate, less degenerate, right? So we want to see what happens to these measures in deterministic non-degenerate models, but also in indeterministic degenerate models, right? So let's take the supes as an example of this. So what this would show, this plot on the left here, hopefully everyone can see my cursor, would be that this is the value of the measure. So the heat map is the value of the measure. So we say that the supes is greatest when the system is deterministic and non-degenerate. In other words, when every cause is perfectly sufficient and totally necessary, the supes measure is highest, right? And it's lowest when everything is totally noisy and nothing is sufficient and nothing is necessary, right? So this is just to show that the measure is kind of behaving. These measures behave pretty well. You have some slightly weird things that occur, like on secondary transitions, you get a lot of negative causation. So by secondary transitions, I mean off transitions. So like if the cause has a 90% chance to produce one effect and a 10% chance to produce another effect, and it produces the other effect, that can get counted as negative causation by a lot of these measures, which I think is fine, but it's just like a little bit weird. And as you can see, so as you go through them, so this is the main transitions, the secondary transitions, how they behave on the average of all the transitions, and then how they behave on the average across the different intervention distributions. As you can see, basically across the intervention distributions just don't matter. Like, let it use the stationary, use the local, use the maxent. My point being here is that there's a huge amount of consilience. These measures basically behave the same. And we don't really need to worry too much about the intervention distribution then, because it kind of just drops out if it always kind of looks the same. So this is how the measures behave. They behave like we think. Okay, so now we're going to look at the same thing, but we're going to be looking at causal emergence instead. And by that meaning that we're looking at the difference between applying the measure at the macro scale of the system versus at the micro scale of the system. And first, let's look at the causal primitives, right? So let's look at the sufficiency. This is just the top left half here. And what you should see, right, is that along this bottom axis, it's scaling by determinism. So, right, this, and it's not sensitive to degeneracy, which is the y-axis, right? The y-axis doesn't matter here, only the x-axis does. And that's because we're looking at sufficiency. So think about it, right? As you make the system more indeterministic, and I'm a microstate, I randomly go to way more different microstates. So of course, my sufficiency is going to be low, right? So my probability of sufficiency, my probability of being able to produce a given effect is quite low. But at the macro scale, I'm always perfectly sufficient because I always just produce the other macro state, no matter what. So that should mean that and when I subtract those two, what I get is that my macro state is way more sufficient than my micro state. And that effect gets larger as my system gets more indeterministic over in this regime. So the more noise I have at my underlying microscale, the more causal emergence I see, because the sufficiency has this, trickle down effect where all the measures are just based off of sufficiency and necessity. The same thing is true for necessity. I won't go into all of these, but let's just take a look at like a given example, like the supes. The supes is a measure I quite like. I think it's a very elegant, simple measure of causation. And when we look at it and we look at the bipartite model and we look at the causal emergence of the supes measure, what we see is that when the model is very deterministic and non-degenerate, so when every effect has a unique cause and every cause has a unique effect, right? So it's like it's just like a chain, right? What you would intuitively think is that this is a great model of the system, right? Like this is like a perfect causal model. Like every effect has a unique cause, right? And every cause has a unique effect. Well, in that case, right, what we see is causal reduction. So we see that actually the micro scale model is far superior than the macro scale, which is exactly what you would intuitively expect, right? But where you see causal emergence is in this far left corner where you see more degeneracy, more determinism. So cases where things are noisy, things aren't sufficient, they're not necessary to produce effects. And so you see a lot of causal emergence where the supes measure scores a lot higher at a macro scale. And what that's saying is that, if the supes is a measure of difference making or causal work, it's just saying that there's more causal work or difference making occurring up at the macro scale. The same is true for eels, Chang, Lewis shows, again, similar effects. The Bitflip measure is a little bit weird in that it doesn't have this nice gradient that the effective information and a lot of these other ones do. But my suspicion is that the way we're to apply the Bitflip measure, we have to kind of put in like arbitrary states to it, and so it might not be the perfect thing. But regardless, the vast majority of these measures behave in exactly the way that we would expect if the hypothesis was that macroscale causation exists, and the ways that it exists is that it's just noise correction. So it's just error correction. So macroscales minimize error in causal relationships, and they do so across essentially every causal measure you can apply. So this is all the measures averaged together. So if you just took all the measures and you averaged them together and you looked at the bipartite model and you parameterized it and you varied the amount of noise, the amount of determinism, the amount of degeneracy, what you would find is a very nice manifold wherein you have no causal emergence or low causal emergence. You basically have causal reduction generally when the microscale is deterministic and non-degenerate. But you have causal emergence in a lot of causal emergence in when the bipartite model is very noisy. And so I think that this shows quite nicely that that basically every measure of causation picks up on macro scale causation. It's just that people didn't really think to look because it's like a weird thing to look at. Like it's not like an obvious thing to look at all until you start modeling systems across scales. But that's like an odd thing to do, and that it seems to really fit the hypothesis of causal emergence, which is that emergence is all about noise correction. And the reason that macro scale models are such good models of the world is that they minimize the noise that you have about the world, about your interventions, about your counterfactuals. They minimize that noise. So I think that this is quite nice. I was quite happy with this. But I want to just end, and I know that kind of walking through a paper is always a little bit rough, but I want to just end with like a bigger picture, which is that, okay, if all these measures agree about macroscale causation, and we kind of take the heart of emergence as emergence is about error correction, it's about noise correction in the transitions of systems or in their causal relationships between systems, what can you actually do with that? Because I think a big thing that people who are interested in emergence from like a more mathematical scientific perspective should keep in mind is that we don't want to do metaphysics. Like that has not really led to anything. Philosophers are still debating about all sorts of things, right? Something becomes a science when it becomes useful. So what can you usefully do with the theory of causal emergence, with this notion that you can identify scales with stronger macro scales, with stronger macroscale causation? So first of all, you can identify intrinsic scales of function. So you can go into the cortex and you can answer once and for all these questions of like, who's doing the causal work here? Is it the mini columns? Is it the neurons? Is it neuronal populations? You can help out with scientific model choice. So another case from neuroscience would be like the Human Brain Project. You want to build a big model of the cortex. Okay, what scale should you build that model of the cortex at? What scale should you kind of think of as if you want to build a perfect neuroimaging system, what scale should that neuroimaging system focus in on, right? It can assist with scientific intervention choice, right? Because it kind of encourages you to think about doing macro scale interventions as well. You can kind of provide better causal explanations, and that's definitional because your causal measures are higher. So of course your explanations are going to be better. It can help reveal or understand opaque systems, like systems where there's no clear scale. And it can also help you build opaque systems, which I'm kind of interested in. Like you can construct emergent systems on purpose. And again, we have got maybe some evidence that evolution itself is doing that. And that we've also got a little bit of evidence that is because macro scales can be like a lot more robust. So if I build a system causally at a macro scale, it's much more robust to like random node attacks because my random node removes the micro node and the macro scale goes on, just fine. So with that, so much thanks to all of you for listening. And then I've had a bunch of co-authors on this journey, ranging from my PhD mentor, Giulio Tononi, and the postdoc I work closely with Luther Albantakis, and it was the three of us who put out the original paper on causal emergence that just used the effective information, or is really just the dressed up supes measure. And then Brendan Klein, who's done some amazing work with network science and causal emergence. Mike Levin at Tufts, who's been thinking a lot about how this makes sense within biology. And then Renzo Camolati, who is the co-author of this most recent paper, and Thomas Relli and I, who have done some recent work looking at synergistic mutual information, which I didn't even mention. This is like a whole other measure, synergistic information, mutual information. It can also be higher at a macro scale. So thank you so much, everyone. And if you've got, I don't know if I went over or what, but if you have any questions, I'll take them now.
Hey, can I ask a question? Can you talk again the definition of scales, and also talk how do you transition from or group the micro scale into the macro scale?
Yeah, so I would say the best way to think about it is that there's there's no single recipe that you have to do in order to, if you have a microscale, right, you can create a macroscale out of it, and you can do so in all sorts of ways. So you could average together elements. You could coarse grain them in some weighted average. You could you can kind of treat them in all sorts of ways. And I'm being very general, and by scale I just mean any dimension reduction of the system, like any alternative description of the system that has less dimensions. But I do think that there are some really important things about scale that I didn't mention that you want to preserve if you want like a fair comparison. So one thing is this congruency, where you want to make sure that the macro scale that you have is actually congruent in the dynamics to the micro scale, right? That like that those two systems are dynamically equivalent. And philosophers have this term that I haven't found a good mathematical replacement for this term, so I continue to use it kind of under duress, which is supervenience. And supervenience is this idea that if you fix the microscale, the macroscale is then also fixed. So it's like if you fix all the quarks in your brain, the state of all the neurons, whether or not they're firing, is now also fixed. So the state of all the neurons supervenes on the state of all the quark cloud, the underlying quark cloud of your brain, right? The underlying microphysics of your brain. So by scale, I just mean anything that any supervenient description, but I've got a couple papers that are kind of like inventive ways to create macro scales. There's a paper with Brennan Klein called higher macroscales in networks, or higher macroscales in networks, something like that. That is all about kind of how to group nodes and networks to create viable macroscales.
Thank you. And so, but you know, when in your experiments, when you compare the in the experiments you presented in this talk, how when you compare micro and macro, how did you define them?
Yeah. Okay. That's a good question. Sorry, my back arrow is not working for some reason. Let me just go back to, okay. So the microscale is this system on the left here. So here in this case, it's a Markov chain, right, with 8 states. It's bipartite. So there's kind of a left side and a right side. And whenever you're on the left side, you might transition to a different state, but you're always going to go to the right side. Whenever you're on the right side, you're always going to go to the left side. So you flip back and forth between these two sides, while your underlying microscale might be what state you're in might be changing. Now, we don't actually even use an 8 node. We use a bigger system than this, but it's just the same system but larger. So the macroscale that we use is the description of this system as simply 2 states that trade on and off. So the left side is just, let's call it state alpha, and the right side is state beta. And you just go from state alpha to state beta and state beta to state alpha. And you do that, that's the dynamics of the system back and forth. And the nice thing about this macroscale is, first of all, that it's deterministic and non-degenerate. So if you just think about the causal relationships, right, they're perfectly sufficient and perfectly necessary, right? Because it's like, I need it to be the other macro state in order to be my current macro state. I needed that to be true, so it's perfectly necessary. And I'm perfectly sufficient to produce the other macro state. Versus at the microscale, right? If I'm at 0, 0, 0, what am I sufficient to produce? Well, I could produce, 1, 1, 0 or something like that, or 1, 0, 1, but I don't know which microstate I'm going to produce, right? I can produce something, but it won't be perfectly sufficient. So the macro scale is like this almost overly simple grouping, but we use the overly simple grouping because it allows us to parameterize and change, all sorts of the underlying noise conditions of the microscale, and the macroscale will remain unchanged as long as it's still a bipartite model.
Thank you, appreciate it.
Okay, Now let's first pass the opportunities to our precious panelists, because we have 4 very distinguished guests today here. Professor Zhang Jiang from School of System Science and Beijing Normal University. He's also the founder of Swarma Club. Professor Zhang, can you open your mic? Thank you.
Okay. Eric, thanks for your very good, very surprised lecture for us. So I think maybe you will feel a little bit surprised to be invited by us, but actually for us, for the Swarma Club, actually your works have been very familiar with some of the members, just because about 1 month ago, we just organized a kind of reading group, and to read all of your papers and about the causal emergence. And we just keep discussing about this topic for about 3 months. Every week we have a kind of talk just like this, but one reader just share the paper and how can we just understand the thing is. But why we just are interested about the causal emergence, this topic, just because actually our club, Swarma Club, actually we lots of members are interested about the complex systems. And you know that actually emergence is a very important topic. And we just found that although you have done it maybe several years ago, but we just found actually there are some progress on the quantitative measure of the emergence. So that's the why we are just so interested about that. So for me, actually, I'm a professor in the School of System Science in Beijing Normal University, and I have done something about the machine learning and the modeling of complex system and the scaling and something like that. So right now, my interest is about how to merge the two fields. One thing is the machine learning on complex system, automatic modeling of the complex system, and the other is the causal emergence. Just because in our club we have another large group about causality, causal science, like in artificial intelligence. So I think maybe in the future we have more and more shared common topics. Yeah, that's why we today we have this kind of lecture. Thank you.
Well, I absolutely love hearing that. That's such a treat to hear. I should probably apply for an academic position at Beijing University or something.
Yeah, you are welcome. Maybe in the future, after the academic, you can just come to Beijing and to just join us. Yeah, thank you.
Yeah, what a treat. Thank you so much for that. That's really absolutely lovely to hear.
Yeah. Okay.
Okay, and we also have Sarah Walker. She's the assistant professor from School of Earth and Space Exploration in Arizona State University. Professor Walker, you may ask a question and start the discussion.
Excellent, thanks. Hi, Eric, it's great to see you. And thanks all for inviting me. It's very exciting to be here. And Professor that just spoke, we've corresponded by email, and I'm hoping that we'll have a chance to meet as well. And chat, so that would be great. So I really enjoyed the presentation and also seeing the newer paper. I'm super excited about reading that. That'll be a lot of fun. Eric, there's one question I have for you though that I keep struggling with in some of the work that we're doing in our group and thinking about applying causal emergence and how to use the theory. And I'm always kind of struck about whether the features we're extracting are features of our models and the way our minds make sense of the world, or are they actually features of the systems we're studying? And you hinted that, well, you made some very, direct statements that it's features of the systems we're studying, but there's also some features of the measures in the way that we talk about applying them that sound like they might be features of our minds and how we're actually regularizing the world. So I'm just kind of curious about your perspective on that dichotomy when we're talking about these kind of issues.
Yeah, it's such a great, also it's great to see you, Sarah. It's such a good question. So, I think that one is that this isn't really just a problem that, oops, did I lose you? Did I lose myself?
I'm still here. Sorry, I had my 5-year-old also knocking on the door when I was talking. So.
Oh, no, totally fine. I think that one, this isn't a question that causal emergence faces alone. Like all measures of causation have this question of, is causation something real in the universe, or is it something that humans kind of read into in the universe? Is it a projection? And I think you can ask this question about a lot of things, like information. You can also ask this question about. I think in the end, my hope is that it essentially doesn't really matter, because if you're questioning the foundations of causation, then that's a problem for people proposing causal measures. Like, this is almost kind of the way that I'm trying to screen this off. This is like, that's like a problem for people who are proposing the causal measures. Judea Pearl, talks a lot about this. I think that causation is like a real natural kind, and that counterfactuals are like real natural kinds, and that it makes total sense to talk about counterfactuals and causation and interventions. But some people might argue against that. But given that, what I'm trying to do in this paper is basically show that, listen, it doesn't really matter what measure you pick, and it doesn't really matter what sort of assumptions you make about how you're intervening on the microscale, which is the same as saying what counterfactuals you're considering. Like, what counterfactuals do you consider, right? That also doesn't really matter. Like, we use the stationary distribution. So we literally let, and I don't even think you should do that with causal analysis, by the way. Like, I think it's really non-causal to say that the probability of a counterfactual should be the stationary distribution of the system, because the whole point of causation is to shake the system out of the stationary distribution by asking, well, what if I did this, right? Like, what if things were different, right? So, but even if you use the stationary distribution, you still see the supes is greater at the macroscale in some conditions. The eels is greater at the macroscale in some conditions. So I really think it's picking out something objective about the system itself, given this big consilience between the measures. But that doesn't mean, and I want to stress this, that doesn't mean that there has to be one perfect measure that everyone universally agrees on. And I think maybe this is kind of a subtext of your question, and I think it's a really good one, which is that what's happened with something like integrated information theory is that it's become a huge dispute over the exact precise measure. And I think that that's bad. And the advantage we have when talking about emergence is that emergence is like complexity. What's the actual perfect measure of complexity? There is no actual perfect measure of complexity. There's like a host of there's a family resemblance of good measures of complexity that all kind of look the same, and they're enough the same that we can have complexity science. And generally, when things are complex, the measures will be high, and when things aren't complex, the measures will be low. But some measures might slightly disagree, right? Like, is logical depth is not the same as the length, the length of your Turing description. Your Kolmogorov information is not the same as logical depth. Those aren't quite the same. Which is the real measure of complexity? Complexity might just be have a bunch of different underlying things, kind of a bunch of different underlying aspects to it that aren't obvious. And so this is what I think about emergence, is that emergence is like, if complexity is real, if this notion of complexity is real, then our notion of emergence should be just about as much as real as that.
So I have a follow-on question, if I may. I don't want to take too much time because I know there's a lot of people here that are probably anxious to ask you questions. But I think one of the issues for me is that a lot of our current theoretical structure actually just doesn't have an account of causation in it to begin with. So it's almost like you as a person are given a bad set of models of the world because they're cast in this sort of lineage of dynamical systems that come from Newton and the way that we formulated early theories of physics, which have no sense, like basically physics has coarse-grained causation out of the universe and everybody adopted that view of the reality, right? So then you're coming in and saying, well, there really is causation there. So let's apply these measures to it and show where it is, which is great. But the kind of interventions you do on the system seem to me that they should suggest ways of constructing better theories. And I'm just wondering if you know, in the space of how you're thinking about applications of it, if you've thought about what is this class of models telling us about how we should construct theories about how the physical world works if causation is a really fundamental thing.
Yeah, it's a really good question because, you know, and I have to kind of, I think I can give kind of a hand wavy answer, or I can give like a better answer. And I think I'll give the better answer. And the better answer is basically that I don't think we should even immediately be talking about physics when it comes to talking about causation. And the reason, and that's really like reductive, and some people don't like that. But the reason why is that if you have like a cellular automata, and you can talk about causation in cellular automata, you can talk about causation, right? It's kind of like, just like there's no, people talk about continuous mutual information. There's not even like such a thing as the continuous mutual information. Like it's like kind of made up. It's not really the same thing as the discretized mutual information. Like Shannon writes down this equation for continuous mutual information, but it's just not the same thing. It's like this weird thing. So and physics is continuous. So it's like, you know, is there information in physics? Well, even set that aside, right? It's like, well, but the information theory works so well in cellular automata and Turing machines and Markov chains and Boolean networks. And these are all things that crop up all the time in science, even regardless of if you're talking about the fundamental microphysics. And now I know you're a physicist, right? So of course your interest is going to be in like something, you know, related to physics, right? But as like a non-physicist, I would also say that, you know, causal emergence can also just be thought of as scale relative. So if I'm looking at a gene network, I might be representing that gene network in this really nice discrete set of Boolean operators. And I could look at my well-defined macro scale. I could use, you know, really nice coarse graining techniques, and it'll all kind of make perfect sense within the system. If you then say, well, you know, let's go apply this to, you know, hurricanes or plasma or like the quantum wave form, you know, I'm going to be like, well, I don't quite know how to do that. And that seems like it requires, you know, it'll require a lot more work to figure out how to best represent causation in physics and things like that. But I don't think that it's wrong to kind of get a working theory. My strategy is basically to try to get like a working theory of emergence that works like in cellular automata. And if you have something that works well in cellular automata, then you can slowly expand outwards the same way that, you know, you start with discrete information theory that's just channels and signals and wires, and then slowly expand out. And now we can talk about information theory much more broadly because a lot of really smart people have done really good mathematical work. But I'm just not, you know, smart enough to kind of immediately figure out any of the continuous application stuff or the physics stuff or any of that stuff.
Thank you. That's great.
Okay, let's pass on to our last panelist, Yue Tao Ye, sorry. He's the founder and director of the G-Tree, Deep Perception.
Hello, Eric. Can you hear me?
Yes, I can. Thank you so much.
Okay. A question for you. We know most models have sloppiness, which means the role of different parameters in the model are not evenly distributed, are not the same. And also, even for a single parameter, the values, the space of the value are not the same. Some part of the value range might have a great effect on the model in terms of intervention and effect. But on the other hand, the basic assumption for effective information is maximum entropy, which means all the interventions are evenly distributed on all parameters and on all values of the parameter. So I'm just kind of thinking of this matter. Is it the only reasonable assumption? What would happen if do we have any other possibility of the assumption of maximum entropy for the definition of EI? Thanks. By the way, this is Max. We talked on LinkedIn, and it's nice that finally meet you here.
Oh, wonderful, wonderful. Thank you so much, Max. Much appreciated. Yeah, what a good question. So I actually have a paper that I didn't talk about that is kind of answering, is kind of trying to answer this. And the analogy, it's sloppiness in models for people who don't know. A lot of that stuff comes from information geometry, and so one option, right? So again, the maxent works really well. Also, again, if you're in like these cellular automata regimes, so like of course you want to kind of consider the set of states within your cellular automata. But you're absolutely right that like if you're in the brain, so we're like now we move from cellular automata to like looking at like a mammalian brain. What's the maximum entropy distribution applied to a neuron? And I always ask Giulio Tononi this because this is in integrated information theory too. It has people never criticize integrated information theory for having a maximum entropy assumption, but it does. But it never gets criticism because the math is more complex and no one understands it. So it's like, what's maximum entropy for a neuron? It's like, well, one physical state of a neuron is that the neuron is like lava, right? It's like, what and you're making the really good point is that like when we go to intervene on like the sensible state space of the brain, we don't superheat neurons as part of our interventions. We don't consider those as counterfactuals because it would be absurd to do so. And that's really like the problem with the maximum entropy distribution. So actually in this recent paper, what we and what I talked about in this other paper, this causal geometry paper, is kind of this notion of local interventions. And the idea is that you do think about maximum entropy as like a sphere around a local point in state space. So it's like if I want to consider my counterfactuals, and I think David Lewis, by the way, has in the end like the best kind of intuitive notion of causation. And his notion was that it's a cause and effect relationships are based off of the closeness of possible worlds or counterfactuals or interventions, right? So it's like if I could change the world in a minimum way, and then I change and I change the effect, then that's what a cause is. But the problem that he had was that he's basically said, I only want to pick the very closest world to make my comparison. And the weird thing about that is that it leads to these weird edge cases. So you can go to the philosophical literature and you can find these really funny conversations where people are concocting these like crazy scenarios involving like nuclear wars and buttons and so on, about like to poke a hole in David Lewis's conception of this super close possible world. And so I say, well, just you avoid those problems, and you avoid the problem with the maxent by just taking a local sphere. So you get all the benefits of David Lewis and the benefits of maximum entropy without doing the full maximum entropy. And so that's what I think that people should do. I think that really there's only a couple sensible choices for how you measure the counterfactual space or assess the counterfactual space, and some sort of like local average or local assessment within like a limited distance. It's almost like calculus, right? Like it's almost like you want to look at this minimum distance, but unlike calculus, you don't only want to look at the very closest point. You kind of want to just look at the range of points around you and see how varying your parameter varies the effect of that parameter, within a sensible range, but not within this crazy range of the max n. But again, one of the big takeaways for this paper is that that choice, at least here, didn't matter at all. So it didn't matter if we use the maximum entropy, this empirical distribution, a local distribution. They're all the same. They all show causal emergence in all the measures except effective information, which doesn't show causal emergence when the system is symmetric and you use the empirical distribution. So effective information is actually an incredibly conservative measure of causal emergence. It's the only one that even failed under some conditions. So yeah.
Bring this up. Among the 12 or more different definitions for causation, did you find any definition that does not give you emergence, but instead the reduction or whatever in the same circumstance, the same condition, I mean?
Yeah, so the only answer is the effective information. And again, this depends on the system. So they all show, they all show, when I say they give causal emergence, I just mean that under some conditions of the system architecture, they give causal emergence, right? So that to me is giving causal emergence, just to be clear. So, because it would be trivial if everything was emergent, that's trivial, I think. And actually, I think that the reductionists, like universal reductionists, are saying something very trivial, right? You have to think of that as a very trivial position. Everything is reduced, right? It's like, no, it depends on the system. But within our model, the only thing that did was the effective information under the empirical distribution. And the effective information under the empirical distribution is mathematically equivalent to the mutual information. And the mutual information is legendarily a measure of correlation, not causation, right? So it's not a specifically causal measure. It's a measure of information, right? So, and actually I have another paper looking at the mutual information because, I think it's like, why would all these measures show causal emergence and the mutual information doesn't? But people have now recently, in the past, 10 years or so, done some brilliant work decomposing the mutual information into 3 parts. The synergistic information, unique information, and the redundant information. And it turns out that the synergistic information and the unique information can both show basically causal emergence in that they're growing across, they can grow at macro scale. So both the synergistic and unique information can be higher at macro scales. And it's just the redundant information that is basically keeping the mutual information from growing at higher scales. And that makes perfect sense, right? Which is that the micro scale, there's so much redundant information that it's like you're double counting, right? Like you're double counting the causally relevant information. So if you basically take the mutual information and separate out just the causally relevant information, which is like synergistic and unique, you see causal emergence with that as well. So
what I mean is, since you are examining different definitions of causality, even 12 different definitions, so did you find any case that for a certain system and a certain fixed condition, different definition give you different direction of causality?
So yes. And
okay.
yes, yeah, absolutely. And this kind of goes back to Sarah's question, which is that, if they all gave the exact same values, then that would be like some incredible triviality, right? It'd be some incredible consilience, right? But they generally give the same manifold, particularly the ones that I think are kind of best. I mean, and I know that that's a bit subjective, but there's far more good ones than there are bad ones. There's only 1 or 2 that I don't think give that sensible results. But it also, the bipartite model is a bit specific. So, what to do with that? Like, there's even cases, actually, hilariously enough, there's even cases of what I've been calling in private, I don't know if I'll call this in the paper, super emergence or super causal emergence. And super causal emergence is
what do you mean?
It's when the macro scale has a positive, because some of these values can be negative, right? You can have negative causation, which is preemptive. So there are some system architectures which you have negative microscale causation and positive macroscale causation for the same transition. So the same thing is happening, microscale and macroscale, exact same thing, but up at the macroscale, you have like a positive value, and at the microscale, you've got a negative value. It's not just 0 or a really low number. So you have like super causal emergence where the microscale is actively trying to prevent the effect, and the macroscale is doing it. So but I bring that up because some measures, for example, don't go negative. So then in those cases, you would have a clear disagreement, right? Where some would show super causal emergence, some would show it's just 0, but I think, overall, some of the measures we even prove, like Pearl's measures, we don't even measure because Pearl's measures are just the same as some of these other measures. So there is a lot of, overlap, this huge amount of overlap. But you're right, there could be cases, but I think to me, this looks a lot like cases of, listen, we don't have a perfect measure of causation. We don't have a measure of causation that every single person agrees on. But we probably have enough of an idea that just like, not everyone agrees on what complexity is. Like, is complexity the length of a bit string? Is it logical depth? What is it? But we have a family of sensible measures. And I think here we have a family of sensible measures, and they give generally the same thing. And even if they did disagree, I'm not sure if that would be a huge problem for causal emergence as a general idea.
Okay. I know I have been taking a lot of time, but I have one more question that I wanted to ask for a long time. I know you are a scientist and at the same time a writer. You write novels. Actually, I ordered your book from Amazon. I just about to start reading it. Because me myself, I have thinking of in the future, maybe I want to write a novel. By the way, I have never wrote a novel before, but I want to ask, how do you manage those two skill sets? What do you need to learn to do that?
Well, lovely. Thank you so much for ordering my book. I was gonna say, so you're the one. I grew up in my mother's bookstore, so writing and reading was always something I was really interested in, and I worked at that bookstore. So I was a bookseller when I was a teenager, and I sold books to people. So I always loved writing, and particularly I love the idea of putting a lot of science into literature, because you don't see a lot of science in literature. You don't see a lot of literature set in the scientific world. You see science fiction, but it's all kind of imaginary science, right? That's what makes it science fiction. So I wanted to do something that was more about real science. So I do think that there's kind of a market for that, or a niche for that. As to how I do it, maybe I'll just say that my graduate advisor wasn't the happiest that I spent some of my time doing that during my PhD, but in general, you've noticed by looking at my scientific papers, I do not write very many scientific papers. So I really am trying to just do 2 to 3 papers a year that I really like. And I don't know if that will work out long term, like in terms of the academic job market. And I don't just do that because I don't have the time, but I do it because I really would prefer to get one paper I'm like really proud of than like 20 papers that are just kind of out there and they make my resume look good, but no one's even citing them or reading them. So one reason is probably, so one thing is just that I try to not minimize my science, but try to just really focus it on just a couple papers. So I'm only doing those papers, but that has some big downsides, so yeah.
Okay, thank you so much. At last, by the way, China, indeed.
I was gonna say, let me know when you're thinking of. Let me know how the writing progress goes. You'll have to contact me and let me know how it goes. But sorry, you were saying.
Oh, I was saying China, indeed, has a lot of career opportunities if you are indeed interested in the future. Actually, I mean, in academia or in other fields. And you are mostly welcome, of course.
Yeah, I mean, you like Beijing sounds better and better. So.
Okay, thank you very much.
Eric, talking about book, we will actually have another thing we want to ask you if the book's Chinese version's copyright has been authorized. If it is not, there are a lot of people in the reading club as well as the community wanted to read your books. So we were wondering if there's possibility that we could help you to translate the book. The revelation.
Yeah, that's absolutely lovely to hear. I would love for there to be a Chinese language edition. Generally the publishing companies are the ones who decide where what markets they're gonna try to push the book in, what national markets, and so they have not done a Chinese translation of the book yet. If someone in your audience is super interested in doing one, I'd be happy to try to help them out or put them in contact with my publishing company, but I can't promise that that they would even get paid. I have no idea if my publishing company would even be interested in that. They're really big companies and they don't really care that much about the individual author, so they're a little bit hard to track down, but it's possible.
But we'll follow up with you on this issue.
Yeah, that's lovely.
Absolutely. Okay, we got time for only one question from the audience. So I was wondering if there is an audience. I saw there's a hand up from Hao Liu.
Yes,
if you want to open your mic.
Yeah, sure. Hi, Eric. Thank you for your great presentation. I learned a lot. I have a question about in machine learning community. People have been working on causal feature learning or causal presentation learning recently on data like images or this kind of data. I was wondering, what do you think are the connection between these two fields and what are the implications possibly from that field? Yeah, thank you.
Yeah, it's a good question. Let me distinguish between causal inference, which is the finding of a causal model, and causal emergence, which is almost saying once you have a causal model and you could create other ones at higher scales, how do you kind of assess causation between scales? So but I'll note that distinction is not as clear as I make it sound. For example, if I am going to do causal inference, I might have to pick a particular scale. I often will do this implicitly. So scientists pick scales of interest implicitly all the time. Funnily enough, with no scientific backing, right? Like it's not based off of anything really scientific. They just say, this is my scale of interest. And now I'm going to do my causal analysis off of that. So a lot of the stuff, some of the stuff in machine learning is doing that, and causal emergence might be relevant there. I'll also say within machine learning and artificial neural networks in general, I mean, one of the things that I've really wanted to do for a long time and turned out to be basically technologically impossible was to measure causal emergence in the brain. And this is actually why I went to Columbia, and it turned out to be very difficult to do empirically. And it wasn't me who couldn't do it, right? Like some of my co-authors were trying, and neurons are just really hard to work with. The brain is really hard to work with. But artificial neural networks, we don't have that problem. And actually, it may be the case that that you can apply the causal emergence framework and create macro groupings out of neurons or neuronal layers. And you can kind of do causal emergence and within artificial neural networks as your model system. And you might find some really interesting things. You might find that, you might identify important macro groupings or macro states of neurons. You're basically getting a different neural network on top of your other neural network, right? Like you're getting a macro neuronal network. Capsule networks, which Hinton came out with, are what I would do kind of naively to create a viable macro scale that you would get high causal emergence in, right? So there's already like hints that this is going on, and that maybe for some of these really big artificial neural networks, they're not a lot of the causal relationships and so on are no longer at the individual microscale of the neurons. They're over coarse grains or groups of these neurons. And that might have really significant impact, because what if I apply a measure? Like, what if I apply my information bottleneck? But what if the neurons aren't even the intrinsic scale function of the network anymore? Maybe the intrinsic scale function is some meso grouping of those neurons. And then my information bottleneck numbers won't make any sense because I'm missing it. The information bottleneck is up at a macro scale. So there's a lot of applications that I'm really excited about. The problem is that they're continuous systems, and I hate continuous systems because they make everything really complex, and they make a lot of measures really kind of complex and have weird boundaries. So I have a paper, if you're interested, where we try to apply the effective information in artificial neural networks, and we do get a working measure out of it, but you have to like discretize the network into bins, you know, and coarse grain it and so on. So it's not as nice as working with something discrete.
Thank you. But like for data like images, is there like a very principal difference between like networks and images data?
A principal difference between networks versus image classifiers?
Yes, just the image data.
Oh, image data.
Yeah.
You know,
like the pixel there will be micro variables, and something like a dog or cat is kind of semantic variable will be a macro variable.
Yeah, that's smart. Like I think intuitively you're correct, but the thing is that, you know, it's called causal emergence for a reason, which is that you need some notion of causation in there, and like static images, right, don't have any causation in them, right? They're just static, right? So it's just strings of data. But if you had videos, it's a little bit different, right? Because you can think of voxels as leading to one another in certain ways. You can think of things like that. So it may be possible to kind of apply it more naively to strings of data, but I think much more likely, which is that, and this is actually, I think, is a big question in macro scales of, a big question when it comes to artificial neural networks, is like, are they picking out the right scale? Like when you think about images, like the ones you're discussing, right? There are really famous cases where you can vary the image in a weird way that a human is undetectable. So it's like you take a picture of a cat, you vary it in a way such that to a human it still looks like a cat, but an artificial neural network that has been trained to differentiate cats and dogs now says that's a dog, even though clearly it's a cat, right? And what's going on there is that the network doesn't have the right scale. And so these questions of scale like are really like meaningful, useful scientific questions, but we just don't have like a good generalized field or subfield, let's be honest, like a subfield that deals with questions of scale and emergence and causation and kind of macro versus meso versus micro level phenomenon. And I really think we need one that kind of looks a lot like complexity science.
Thank you.
We're almost running out of time, but there are two questions from the column of the audience. You may respond them shortly. The first question is, emergence causation equals microcausation minus microcausation. Does that based on assumption that macrocausation is weaker than microcausation? Cannot we give easy a broader notion that is microcausation stronger than micro? I'm not sure whether I understood the equation.
Yeah, so the equation is macro minus micro for causal emergence. If the value is then negative, that would be causal reduction. So it's just the difference between, just imagine them as two amounts. So I've got my macro scale causation over here and my micro scale causation over here. If my macro scale causation is greater than my micro scale causation, then I have, for the same transition, so the same thing, this is key, like you're comparing the same thing. It's just two different levels of description of the same thing. But if my macro scale causation is greater than my micro scale causation, that difference is the causal emergence. If my macro scale causation is low and my micro scale causation is high, then I have causal reduction. The microscale is a better causal model. It does more causal work. It's a better explanation. So it's just the difference between the two values, and whether or not if the microscale is greater, you call it causal reduction, and if the macroscale is greater, you call it causal emergence. But
Okay.
I understand that the theory involves a lot of introducing this involves introducing a lot of jargon, so it's like relatively confusing.
Yes,
Yeah,
and then
thank
the
you.
second question is causal emergence to reduce the complexity by microscale?
Yeah, so if there is causal emergence, you were comparing a macroscale to a microscale. That macroscale, by definition, is less complex in that it has a smaller number of dimensions. Like, it's a coarse grain of some kind, right? Like you've lost some sort of dimensionality. So by definition, it will be less complex. But I want to differentiate causal emergence. Let me take this opportunity to differentiate causal emergence from like a broad non-committal view that macroscales can be useful or interesting sometimes. And in that broad non-committal view, which a reductionist can hold, they might say something like, yeah, listen, what macroscales do, like the reason why, the question is like, science is almost entirely macroscales. Almost no one in science deals with ultimate physical microscales, right? Which is like the ultimate physical microphysical laws. No one deals with those. All the entities we deal with, cells, neurons, animals, right? People and economics, they're all some macro scale. And there's then the question is, why is science filled with entities that can be completely reduced, right? And the answer that the universal reductionist has to give is that they only are used as a shorthand. It's only used because it's easier to talk about macro states because they're not as complex. You don't have as big dimensionality, right? You're like, how could you really specify all the atoms in a cell, right? And what causal emergence says is that, yes, that could be one reason, but another reason is that my causal relationships between macro scale entities in the world are much more reliable, stronger, more informative. The causal power is greater when you look at the causal relationships between these entities. And that's one reason why science treats these things as fundamental and not something that can just be reduced. So complexity is certainly a part of it, but I want to differentiate between kind of the complexity explanation of why macro scales are useful or interesting, and then the causal emergence explanation, which says that there's something that goes beyond just that macro scales are less complex and easier to work with.
Thanks, Eric. I have a question about the intervention probability or the intervention distribution you've shown us today, because according to your recent work that you tried many different kind of intervention distribution and showed that doesn't matter. But you also mentioned that there exists some bad distribution, such as empirical distribution, because that will lead the causal emergence disappear. So my question is, so assuming, so that basically means you are changing some probability, and you don't inherit the probability at micro scale. So if you inverse this process, what you are doing is such as manipulating the experimental distribution. So I want to know, what can we learn from this difference when you change the experimental distribution?
Yeah, so this is not what's happening, right? So just to be clear, the empirical distribution, when I said it's bad, so first of all, to address the first point, when I said the empirical distribution is bad, I don't mean for causal emergence. Causal emergence is shown in the empirical distribution across pretty much all the measures of causation that we can show, using the same distribution for the macro and the micro scale. So there's no differences in how the macro scale intervention distribution is treated. Like those are identical. What I mean by that is that in general, for all measures of causation, I think the empirical distribution is bad. So not for causal emergence specifically, for measures of causation. because it's kind of like, how can I understand the causal structure of something if I don't intervene on it to change how it's working, right? It would be like, I only allow the system to do its own thing and I never perturb it or intervene on it, right? That's the empirical distribution, is that I'm not doing anything. And but I think you bring up a really good point. If it were the case that that we were like changing something about the probabilities of the macroscale, and this was causing the causal emergence to not occur, this would be a problem. This was Scott Aronson, the blogger, is like the first kind of criticism of causal emergence was somewhat similar to that, which is that the effective information, it has this requirement about how you do the intervention distributions, and if you do it in this empirical distribution, then the causal emergence stops working. But again, that's only in the case of the effective information, and it's only for the empirical distribution. So in all the other ways that you can do it, you see causal emergence. So it turns out that effective information is just a super conservative measure. The other measures are more liberal, and you actually see causal emergence across them. So I think that it's very interesting to think about what is like the best intervention distribution, right? I think that that's a really interesting question, but it's actually a question that the causal emergence framework doesn't need to answer, luckily, because it's kind of a tough question, because it turns out we can just look at all sorts of different distributions, or at least the three main kind of sensible ones, and we see causal emergence in all of them.
Yeah,
that perfectly answered your question. Feel free to follow up.
Yeah, I wasn't intent to criticize of this your maximal entropy distribution or something of that. I just think that this process of picking some low probability micro state to a higher probability to intervene to do intervention at macro is an interesting thing, such as if we just measure what we do every day, then the switcher and the light, this pair will be very low probability. But if we coarse grain it into a macro scale, I believe that these two things will be a standalone state, and in this way, actually, we are increasing the probability. So I think this might be something interesting behind this process when we increase the probability.
Yeah, that's really smart. Okay, I understand your question better now. So I'm sorry for misinterpreting it. And it's, by the way, it's fine to criticize the maximum entropy distribution. I criticize it in this paper, right? But you should offer a sensible replacement, and sensible replacement is not the empirical distribution; it's the local distribution. Regardless, so you bring up a really interesting point, and this is something that the effective information does well, and some of these other measures don't do as well. Which is that, let's say I take the universe as one big macro state, right? And I coarse grain it, and it's a macro state that keeps itself on, right? It's your, what did you say, a steady state? How did you say it?
Standalone state.
Standalone state. I've never heard that term before, but I think I know what you mean, right? It's a state that keeps itself in the same state, right? So you coarse grain the whole universe into a copy gate that maintains its own state, big macro state universe. Perfect determinism, no degeneracy, right? So we have causal emergence. Well, this seems like problematic, right? But the thing is that you didn't have to coarse grain that high to get very high values of determinism and degeneracy. So what you can do is, for these measures and the effective information has a built-in size kind of term, such that the effective information of grouping the whole universe would be low, very low. So you would never do that. It would never be causally emergent. But for something like the eels or supes or these simpler, more probabilistic measures, you might be able to do something like that. And then you can kind of argue that maybe causal emergence is kind of weird or trivial, or is giving you macro states that are too big. Like it's like everything's just shooting up to the absolute macro, right? But what you can actually do is again, something very reasonable, which is say, well, no, what you want is the scale at which you've maximized these values, or at least are very close to maximizing these values, while not reducing the dimensionality of your system more than you need to. So in other words, if you were coarse graining up, you would reach a point where everything is very deterministic and non-degenerate well before you've grouped everything into the entirety of the universe, right? And then at that point, you wouldn't be increasing your determinism and degeneracy, or you'd be only increasing it by minuscule amounts, but you'd be throwing out the dimensionality of your system. You'd be throwing out the size of your system. So I think when you talk about like using these measures to apply them directly to light switches or the brain or what have you, to identify like emergent scales of function. So to use causal emergence to identify some emergent scale in a system, what you should do generally is coarse grain until you are getting diminishing returns and your scales, and you're not throwing away scales anymore. So, so I think that's a very interesting question. And I just said an idea of mine that now I hope no one else publishes first, because at some point I want to do that paper. But if that sounds interesting to anyone, contact me, because that's a paper I'd like to do. And I think it'll look a lot like a small world network, where in small world networks, right, there's a really famous result by Strogatz and Watts showing you can create a small world network by you have clustering and path length, and you minimally vary the path length, and you get a small world network, right? But you can preserve the clustering. So what I think that we can show is that systems have emergent scales when you are coarse graining them, and you find the scale at which you have maximal determinism degeneracy, and you aren't getting diminishing returns on that by shaving off dimensionality. So it's like you're balancing how big your model of the system is with how deterministic and non-degenerate your causal relationships are, and you find the maximum of both, right? Like you want to preserve as many system states as you can, so you're not just coarse graining everything bigger and bigger, but you're also still maximizing determinism and degeneracy and these other causal measures, these causal primitives. So it's kind of like focusing a camera, and you're finding the right focus to it. So yeah, really good question.
Thank you very much.
And I think here we should just set some constraint on the coarse graining method, because I have tried to maximize the EI, effective information, on the macro dynamics. However, we allow the coarse graining method can be optimized also. So in this way, actually, we although the scale is not so large, however, we can just optimize to a kind of causal graining method and the macro dynamics. However, it is very trivial. We cannot have a meaningful causal emergence and meaningful macro dynamics. So I think we must set some limitation constraint on the coarse graining method.
Yeah, so that's a great question. So the idea that I have for that of like, so basically one way to think about this, right, is that causal emergence almost works too well in that you just group everything up into a macro state. But yeah, what you should find is that you'll be getting diminishing returns past some point of grouping. So it's like let's say I have one scale. I have a mesoscale, an in-between scale between my micro and my total macro. And my mesoscale has, 100 dimensions, and everything is 99% sufficient and 99% necessary, right? Now, if I coarse grain the entire thing, I could make a system that has one dimension, yeah, right? And is 100% sufficient and 100% necessary. But it's like, but you've messed up, right? Because you're in this domain of diminishing returns. And so we should think about emergence or emergent scale, like an emergent scale, finding an emergent scale, very much like small worldness, wherein it's this sweet spot. So systems that have distinct scales have sweet spots where you can quickly maximize the determinism of degeneracy by throwing out some dimensions, and then you get to a point where the more you do it, the less gain you're getting. And a measure like effective information or integrated information will pick that up. But here's the trick. You don't even need those measures to make that claim. All you need is to weigh your causal primitives, which is the foundation of all these measures, by the dimensionality. So really, it's just the causal primitives weighed against the dimensionality and looking for this point of diminishing return. And these other measures will pick up this sweet spot, this mathematical sweet spot of when a system has an intrinsic scale function. But you can just do it off of the causal primitives. And I think that in the end, that's going to be the most powerful way to do it, because it's the most it's the most agnostic. You don't have to buy a particular measure even to buy that this is the scale of the system that you're looking at.
I have
think
tried
John's
one. Oh, sorry.
I just think John's question is related to another potential problem of general coarse-graining, because suppose you have a system that have redundant variables, then you want to coarse-grain and require it to be like causal emergence or maximize effective information. Then we are free to pick up this which one of the redundant variables to compute the macro variable. So that might be a problem, since many real model have many redundant variable, and when you coarse-grain it, even you successfully coarse-grain it, but it's a machine learning and you don't know which variable it will pick.
Well,
yeah,
you don't need to represent. You can represent some summary statistic over your redundant variables. So some people wonder, they're like, is it really the case that some systems even have a scale? Like maybe scale is something that's kind of made up. The clearest cases are equivalence classes. So if I've got some system where this is basically the bipartite model is an equivalence class, but it's like every state here does the exact same thing. And it's just like a ball of states that all do the exact same thing. And over here, I've got a ball of states that all do the exact same thing. And over here, I have a ball of states, right? The obvious macro grouping is you group all that ball of exactly equivalent states into one, into another one, into another one, right? So in a sense, redundancies make the best coarse grains, because if everything's equivalent, then you can just do some summary statistic like an average, or if you average all those states together, you get the same state as each and every one of them, right? Because it's an equivalence class. So in like a Markov chain, the redundancy actually makes for great causal emergence. I mean, it's the easiest way to get it. Like, I mean, I generally start my papers by being like, let me make an equivalence class of some model, right? And then work backwards from there, because I know that that's going to be the recipe for creating the best scales. But if you're talking about machine learning, which you mentioned, or like more complex cases, then exactly what we mean by micro and macro, need to be re-examined, and what counts as redundant versus not. But like in like a Markov chain or something like that, that isn't a huge problem.
Yeah, I have tried one of the solution is, so we can force the whole pipeline, the whole channel, to just predict the macro states in the future. So in this way, we can force the coarse-graining method not so arbitrary, because you must rebuild, reconstruct the macro state. So in this way, we can, in some sense, we can solve the question.
Well, that's quite interesting. Yeah, that's interesting.
Yeah.
I need to look at the specifics of how you're doing the
I can
training the Macroscale, but that sounds interesting to me.
Yeah, I can tell you the detail. I just finished a manuscript of this. After the meeting. Yeah.
Okay. Well, we are running out of time, and really, I feel really bad to disrupt the this amazing discussion.